Hi everyone, I'm Veda Shankar and part of the community team at OmniSci. Happy to be here presenting on how we integrated OmniSci with StreamSets to come up with one of our best demos with the F1 game. As part of, most of you, since you're dealing with data pipelines, you're not any stranger to the growth of data and, how it's, there's a widening gap between the, the computational power that you need to analyze this data and the data growth. And with CPU-based systems, which is predominant in most of the data centers, that gap is just widening, and it's just going to get worse over the years. Now, if you look at GPU performance, it's actually growing at almost like 50% year over year compared to the CPUs, and it actually has kept in pace with the data growth rate, and and if you compare CPUs and GPUs. You'll see that even though a CPU individual core has much more processing capabilities than a GPU, just because the sheer number of GPU cores, you can actually get so much more done. So in this particular slide, you can see that you can get like almost like 20 tasks per nanoseconds versus 4,000 tasks per nanosecond. So that's a orders of magnitude greater on a GPU-based system than a CPU-based system. So just like that, we also have the memory bandwidth in this particular chart with the SSDs at 1 to 2 gigabytes per second, while the CPU RAM is around 70 to 120 gigabytes per second. But if you look at the GPU RAM, the bandwidth is around 1 to 6 terabytes per second. Again, orders of magnitude faster. Only thing, it's more expensive and limited, much more, like less number of gigabytes compared to your CPU RAM. So considering that you have fast computation and also you're able to read, so you can actually, you're able to read faster from GPU memory, and also at the same time you have the computational power to process the data. So all this led to Todd Mostak, who's the founder and CEO of OmniSci. He realized the capabilities of GPUs early on during his research at MIT when he was analyzing the billions of tweets coming out of Arab Spring, and he came up with one of the most fastest data analytics and visualization platforms. And it basically harnesses the power of GPUs and to kind of interactively explore really large data sets. And so that's what OmniSci does. It is a data analytics and a visualization platform. How many of you have heard about OmniSci or used OmniSci or seen a demo? Okay, I see a few hands. Okay, good. And do you encounter a lot of folks in your customer base who have GPUs based system, or? Yes, a few? Okay, good. So, as we are trying to see who is a good candidate, for a product like OmniSci, we find that there are certain characteristics that are associated with the data set that makes it very ideal for OmniSci-like product. So, large amount of data, big data, and also kind of, you have like data coming at you, like so typically a streaming data set using Kafka. And then also there is some kind of a location and time component to it. And so we need an agile methodology to kind of handle this ever-changing nature of this fast data and be able to interact with it and analyze it without any pre-aggregation and indexing. So that's the key. So OmniSci, we just take in raw data and you're able to analyze it just because you can do things so much more faster. So you don't have to downsample anymore. So it's a completely different paradigm, and once I show you a demo, you'll see it in action. So we came with this terminology called VAST, which again stands for that volume of data and the agile nature and the spatio-temporal component. And most of the data, if you think about it, even in case of say Uber, every 30 seconds your geolocation is being sent along with other metadata. So there is always a time and a space component, and you want to be able to have rich graphics capabilities to render these geospatial charts. And that's one of our main advantages of OmniSci. And so how do we do that? Yes, we do have the power of GPU, but at the same time there's a lot of software smarts which allows us to achieve the performance that we do. And one is with the memory bandwidth, as I mentioned. So we kind of make sure to keep the columns that are in play as long as possible in the GPU memory. So initially when you do a query, the data has to come from your SSDs to the CPU RAM and to the GPU RAM, but once it's loaded, most likely your next query is also going to involve some parts of that column, and so it's already resident in GPU. So now it's in like sub-seconds. Now at the same time, of course, we have done a lot of optimization around the analytics operations in SQL, like the where operation for filtering or segmenting using group by. So those are all like vectorized and highly performant. And even in a CPU mode, you'll find that OmniSci is at least a few orders of magnitude faster than your typical databases. Now we use a technology called LLVM for compilation. So we create an intermediate code, and so that way we can reuse these query plans. So when you're just changing some of the literals in your SQL statement, we can just use a pre-compiled version, and at the same time dynamically we can change executing on GPU versus CPU. Now at the same time, GPUs were created for rendering graphics. So now when you're running a query on OmniSci, your results are going to be sitting in the GPU memory, and we can make use of the GPU graphics pipeline to render that. So we use an open source specification called Vega, where you specify how this memory is to be rendered. So it's using JSON, so that is sent by the client system. It renders the data in GPU frame buffer and then sends back a PNG, which is just few kilobytes, back to the client system. So you'll see that you're rendering like millions of data points in sub-seconds, but it's actually you're getting just a PNG. But then the PNG is coming back with metadata information, so you can still select the points on the map. Okay. So this is the high-level architecture diagram. So OmniSci consists of 3 parts. The foundational part is this columnar store, database that's fully SQL compatible, and that is open source. As I mentioned, we use the Vega specification for rendering the data, and so that's the rendering component that talks to Immerse. Immerse is our browser-based visualization platform. Think of a Tableau or a Power BI. It's very similar to that. You can create. Only thing is, you can create some phenomenal choropleths and line maps with millions and billions of points. How many of you have, kind of have a background in, using Tableau or Power BI? Oh wow, okay. A lot of experts, so go easy on those questions, okay? Now, also on this one, as you can see, we can support streaming data, and we have connectors like JDBC, and that's exactly what we use in the F1 demo. We use we created 3 pipelines using StreamSets, and the last of the pipeline, after does the transformation, it basically uses the JDBC connector to write the records to the OmniSci table, database table. At the same time, we have Python APIs and also like JavaScript APIs. It's possible for you to use a Tableau or a Power BI and use as a front end and use OmniSci as a back end. So you can run queries and pull data into those BI solutions. And OmniSci was known as MapD. We changed our name last year, mid last year. So some of you may be familiar. And even today, like some of the components, like our Python API, is still called PyMapD. So if you run across it, you just know it's the same. Okay. Time for a demo. I'm going to show you a demo of the New York taxi data set, which is very popular even for your machine learning. This is one of the first data sets that people use. So in this particular case, we have 1.2, almost close to 1.2 billion rows of New York yellow cab rides from 2009 to end of 2015. And if we go and look at the data, so for example, so that's my table, and if I go to the table, you can see that it's got like about 1.18 billion rows, and it's got like 62 columns. So these range from all the way from the pickup location to the drop-off point, how much was the fare, a lot of lat longs and all that stuff. Right? So there are 62 columns. So when you say 62 times 1.2 billion, that's a lot of data. But when you're trying to analyze a certain aspect of this data set, you'll be only dealing with a few columns. And as you'll see, once those columns get loaded, it's like blazingly fast as you query the data set. Now, another cool thing about this particular demo is how we are, I should have refreshed all my screens. Is in this particular choropleth, what we're doing is we are doing a geo join between the taxi data set and the pickup the building data set. The pickup building data set is coming from the New York City building IDs. It has like 1 million polygons. So as you can see, there's, you can see at the bottom, there's multi-polygons, and there are like 1 million of those New York buildings, and there's a building ID. So what we do is we do a geo join on the fly as you are exploring this dashboard. We do a geo join between the building ID that are part of the pickup locations from the taxi ride with the polygons coming from this New York City building table, and render those polygons on the fly, and it's all done again sub-second. Now all this is done, there is no pre-caching, no pre-indexing. It's just raw data. As you write more data into it, it's going to be used. So as you can see, I put the inspect in the browser, and as you can see, there are SQL statements as I zoom in. So there are raw SQL calls that are just going out to the database, and what happens is as I zoom in, it's setting the boundary, the bounding box for what are those geolocations that need to be rendered, and it's part of the SQL statement that goes back, and of course then it updates every single chart in the dashboard. This feature is called as cross filtering, so that way any change on a single chart will actually impact every other chart in the dashboard, on the dashboard. So let's go back to our demo. So here again the color, we have colored these polygons based on the tip. So again you can analyze various kinds of data, right? Points. Here we are trying to analyze the tipping pattern, for those taxi rides. And so we have this choropleth where the polygons are rendered with and colored based on the tip percentage. So the redder it is, they've actually spent more, green, more, they paid more dollars. And we can see that Brooklyn actually is, better tippers in Brooklyn than in Manhattan. The other thing is over here is a line chart where we have the x-axis has the date and the y-axis has the tipping percentage. As you can see, it's been slowly going up to the right. And then we have the histogram of the distribution of the tips. And then also a pie chart with the mode of payment, whether it's cash or credit. Again, these are all like pre-Uber days, right? So definitely a different time where people use a lot of cash. And again, the average tip. And here's the heat map, which basically shows again, the pattern of tipping based on the time or of the day or the day of the week. Now, one thing that we notice here on this particular line chart is a dip every December around the Christmas time. So my question to you folks is, we want to analyze this, right, in real time across this 1.2 billion records. Can you, do you have like a reason why this would be dipping every year around Christmas time?
People spend all their money on Christmas gifts and they don't have enough money
for the cabbie.
Exactly.
Okay, that's a good one.
They don't travel.
They don't travel. Okay, no, but this is based on the people who travel. This is a tip percentage.
Maybe they hand out actual cash.
Okay, that's a smart man. Yeah, so there are lots of tourists who may not have credit cards, and they are handing out cash. So let's confirm that. So one of the interesting things that I see in this histogram is I should have seen a much bigger like a peak on 20%, right? But then instead I see that there are lots of abnormally there's a huge distribution around the 0% tips. So if I highlight that, so all I did was just brushed across that, so that selected it, and immediately you notice that the cash on the pie chart went up. And so again, to kind of prove that, we can clear this filter by clearing it here. And then what I'm going to do is I'm going to select or unselect. So here I'm basically doing select all those records where the mode of payment is not cash, right? So that's what I just did. So now all we have is just the credit card paying folks. And now you see that it's very flat, and then 20%ers are the norm. And also you see a nice spike here around 2010, beginning of 2010, where it jumps from almost like 15% to 20%. Any clues there? That's when the New York cabs gave that easy button, right? 20%, like nice and bold, So so people are kind of took the easy way out. So so basically this is to highlight, we have few other demos. So if you go to OmniSci/demos, you'll find quite a few interesting data sets. Some of you guys play games, you find NBA data set. There's also like a huge, like a 10, 12 billion row data set for shipping data. So you can go and play with those. So let's, okay. Now, how do you get OmniSci? How do you deploy OmniSci? So yes, we are an open source, so you can download the OmniSci core database from our GitHub and compile it. There are lots of blogs that we have written on how to compile it on different platforms. And There is also a SaaS offering where we are hosting it in our cloud, and that would be like the easiest way where because most of the time the challenge is to get a GPU based system, right? So here for 15 days you get like no credit card necessary. You can simply go to omnisci.com. On the upper right hand side there'll be a cloud button. Just go click it and you'll have your own instance in the cloud with a GPU, a single K80, NVIDIA K80 processor, right? The third option, of course, is you can get an enterprise license. Again, that's also available for 30 days, and in certain cases, if you're doing something interesting, we would be happy to extend that. Now, we are here to talk about StreamSets and our wonderful F1 demo. One of the reasons we embarked on this project was, again, it was Randy's idea. We were struggling to get some large telematics data set. So I went and got some test demo data set from Virginia, but it was like 300K rows, not very interesting. And most of the folks who are doing autonomous driving, they're very, very protective on their data set. So he came with this idea of using the F1 racing rig which actually spews out so much of telemetry. So we set it to the highest mode, which is like 60 hertz. So it's like spewing all kinds of telemetric data, every second. So again, one of the things that we wanted to do is when you have all the streaming data coming in, we wanted to decouple the collection of the data from parsing and ingesting into OmniSci. And that's where I think Randy spoke with Pat, and he got a lot of guidance from your Slack channel and from Pat, and he found that StreamSets was such an easy drag and drop to create different data pipelines, and it was actually quite a breeze, and it's working beautifully well. Now we have put together all the scripts and the code in the GitHub, so you can download and take a look and contribute and expand on it. So these are the different open source projects that we're using: Kafka, StreamSets, OmniSci Core database, and we are using the Plotly, basically for rendering the actual UI. Of course, it's using our Python API to basically get the data from OmniSci. Now, we have created basically three pipelines. Let me explain it because you're all, most of you are familiar with StreamSets. I'm going to go directly to your user interface. So if you go, the first one is basically to listen on a UDP port. And as these packets are coming, these are binary packets. So what we're doing is we're taking these binary packets and putting it as a Kafka, stream called F1 packet stream. Now, the next one is actually more interesting. So here we are taking these binary packets and making use of the Groovy, encoder here. So where is that? Parse binary. Oops.
On the left side configuration.
Yeah, on my left, yes.
There's
Configuration. Yep. And then there's a
stage again.
yeah, there's your Groovy, and that's the code. So basically, there is a jar file associated for the deserializer, which basically taking this binary struct format that's coming with the data from F1 and then creating a JSON string. And then it's doing some other manipulation and then again writing it to Kafka, creating another stream called F1 packet stream JSON. And the final pipeline is the one that basically takes the sorry, wrong one. So if you look at this one, what we have done is in this particular pipeline, we look at the packet ID and then there are 8 types of packet IDs, and we send out to 8 different individual pipelines, and some of them actually have arrays, so we have to pivot and create basically individual records. So we flatten out those entries, and then we finally enter it into 8 different tables on OmniSci. So in total, like every minute, we are producing about 14 megabytes per minute binary. So once you write it in JSON, that translates to around 280 megabytes per minute. So finally, by the time we enter it, it's about 5,000 to 6,000 records per second across the 8 tables. So that's a lot of data, and we've been using that to create our own data set, which is soon going to be 1 billion rows. So just by taking our rig to different meetups and events. So I know we have just like 1 or 2 minutes left, so I just want to quickly show you that there are other APIs and entry points that you can investigate. Because you're also in this data space. So we support geospatial features, and it's really, really cool. When somebody gives you a lat long in float, you can actually create a geometric point, and suddenly now you can do so many SQL operations on it. So it just opens up a whole lot of ways to explore the data. And PyMapD, as I mentioned, is a Pythonic interface. We also support arrow-based, GPU data frame. We are working closely with NVIDIA on the Rapids initiative, so that way all the data remains in GPU memory as you are taking it from OmniSci and putting it on the machine learning pipeline. So it's like basically GPU end-to-end, in a machine learning, pipeline. And I uploaded this deck on SpeakerDeck, so there are links to different blogs that can lead you to the GitHubs, for the code. Again, this is a PyMapD, and then this talks about the Rapids. And finally, just also want to let you know that there is a MapD charting API. Again, open source, and there's a blog that that will point you how to use it. So that way, you can still make use of the OmniSci database. You can still use the rendering engine, but you can embed those choropleths or line maps in your own dashboard. So you could create your own HTML and embed those. And of course, come to our community page, which is community.omnisci.com, and also give that omnisci.cloud a try. So that way you'll get started.